Very good morning to all of you. In the last lecture, we started to discuss about the concept of displacement current. So, I would like to recall some of the discussion that we had in the last end of the last lecture, because this is a very important concept that we must understand very clearly. So, we showed that Ampere's law in this form Ampere's law, which we had obtained before and used for calculation of magnetic fields produced by currents. The Ampere's law in this form has some problem, some inconsistency. To show this, what we had done was we had taken a pair of capacitor plates here and we look at charging of the capacitor. So, there is a current flowing in as a function of time and charges the capacitor plates. So, the objective is to find out what is the magnetic field, say at this point. So, what we did was how do we normally do? We draw a loop, we take a loop of integration, a circular loop around the axis and calculate the left hand side, which is integral b dot dl. Now, in this example, because of a straight wire, because of symmetry as we have discussed earlier, the magnetic field will be azimuthal and so I can actually integrate this left hand side. Now, what is the right hand side of this equation? The right hand side involves the current that is passing through the surface whose boundary is this curve. Please remember that on the left side we have an integration over a line integral, that is integration over a path. The right hand side has the current crossing the surface, of which this line is the boundary. So, normally what we tend to do is to take the surface to be the plane surface crossing the wire, and so the right hand side simply becomes mu naught times the current that is passing through the surface. And we had used this to calculate the magnetic field surrounding a wire and obtained various different magnetic fields. Now, the problem is that in this integral on the right hand side, if I see the current enclosed, there is no necessity that I need to choose this surface. All that is required is a surface whose boundary is this line. So, I could have chosen, for example, if I draw the same capacitor here, is the plate capacitor plate here coming in here. So, this is my loop which I have taken. I could have chosen another surface. The surface I could have chosen is like this. This is the surface. So, this is like a box with a hole here in the center and this is my surface now. The surface encloses the capacitor plates, but does not cross the wire. So, when I look at this problem, it seems that the current enclosed is 0, because there is no current crossing the surface. This surface is not crossing the wire is not crossing the surface, which means that there is no current crossing the surface. So, with this argument it looks like the right hand side is 0. So, obviously, I cannot get two different results for the magnetic field depending on the surface which I choose for integration or for calculating the current enclosed. So, there is an inconsistency in this. So, we solve this problem, or we try to analyze this by using the following argument. Now, let me call these two surfaces. So, let me draw the figure again here. So, I have this capacitor plates. So, I have this loop here. So, let me call this surface S1 and let me draw another surface. I call this surface S2. There are two surfaces which I take. Now, for surface S1, current enclosed is equal to I, because that is the current which is crossing the surface, and for S2 the current enclosed seems to be 0. So, that is the problem here. So, we actually resolve this issue by doing a following calculation. Now, look here, for the surface S2 there is a magnetic field which is within this between the capacitor plates, sorry, electric field between the capacitor plates. So, we calculate the electric flux through S2. So, electric flux is integral E dot dA, and as we showed last time, it is electric field into area. So, if I take a surface like this of this shape, the electric field lines are going like this, and if I neglect edge effects over the capacitor, the electric field is uniform across the surface area of the capacitor plates, and so there is electric field in this area of the capacitor plates and the electric field into area. And I know from an earlier discussion that the electric field is nothing but sigma by epsilon 0, where sigma is the charge density, charge per unit area. So, sigma into A is nothing but q by epsilon 0, where q is the charge on the capacitor plates, sigma is the charge density, charge per unit area multiplied by A, the area of the plates, gives me the total charge contained on the surface of the capacitor plates. So, that is q by epsilon 0. So, now I calculated the current I is equal to dq by dt, which according to this equation is nothing but epsilon 0 d phi e by dt. So, the current that is flowing into this wire into the capacitor plates is exactly equal to epsilon 0 times the rate of change of electric flux through the surface. So, I can actually modify Ampere's law to the following equation. So, if we write integral B dot dl is equal to mu 0 times, now I will call this conduction current, the current that is actually flowing through the wire, I will call it as conduction current. So, this I call as conduction current to differentiate from another current. So, that is a conduction current, that means current that is flowing because of electrons movement, plus I add another term which is mu naught epsilon naught d phi e by dt. So, I have just added this term into this equation to modify Ampere's law. So, this is called modified Ampere's law. Now, what is this? If I look at this equation, if I take the surface S1 for integration, then the second term is 0 and the first term is mu naught I, which is current flowing through the wire. If I take the surface S2, the first term is 0 and I get only contribution from the second term, and second term is also mu naught I, the same term as the first term. So, if I modify Ampere's law to this equation, then I find that whether I use surface S1 or surface S2, I get the same value of the right hand side, and the analysis becomes independent of the surface that I choose to calculate current enclosed. So, this was the modification that was made by James Clerk Maxwell, and this equation is the modified form of Ampere's law. Modified form of Ampere's law. It includes two terms. One is this term called the conduction current term, and the second term is what is called as the displacement current. So, I call the displacement current is I d is equal to epsilon 0 d phi e by dt. So, that is a displacement current. So, I will write this equation as integral B dot dl is equal to mu naught times I conduction plus I displacement. So, this modified form of Ampere's law will help me resolve the problem, and this is what James Clerk Maxwell did, and he modified Ampere's law to introduce this displacement current term, and this displacement current is nothing but related to the rate of change of electrical flux through the surface. Now, I must mention here that there is no displacement taking place, it is just a definition here, and in free space there is no displacement, it is still called a displacement current, and that is the modified form of Ampere's law. And using this, I can use this law to calculate using any particular surface. I can also define a displacement current density. Current density is the current crossing per unit area along a direction perpendicular to the area, and that is, I can define the displacement current density as epsilon 0 d E by dt. So, this is the displacement current per unit area perpendicular to the area that is flowing, and that is called the displacement current density. And just like conduction current density, we have a displacement current density which is J d is equal to epsilon 0 d by dt of the electric field at that point. So, the displacement current can vary between point to point, because the displacement current density can vary from point to point, because the electric field itself can be varying from point to point. So, in general the electric field is not uniform, the electric field is non-uniform, and a non-uniform electric field can give you a non-uniform displacement current density. And of course, if I integrate over an entire area, I will get the total displacement current. So, we started looking at some example. And the example we started looking for is a capacitor with circular plates. So, that is a parallel plate capacitor with circular plates. So, let me assume the radius is r, and the electric field here. So, the current is flowing like this, flowing out from here, and the electric field between the two current plates will be like this in this direction. So, if I draw in this direction, if the electric field is pointing downward, I choose. So, that is the electric field pointing downward. This is the looking at the capacitor plates, and this is the radius r. Okay. So, I am looking at the capacitor plate from here. So, the electric field is pointing downward, and so I want to calculate the following problem. The following problem is, because the electric field is changing with time here, I want to calculate what is the magnetic field generated between the plates of the capacitor at this point, for example, at some distance from the axis. This is the axis here, some distance from the axis, and outside. So, we did this problem in the last class. So, what I do is I take, if the radius r is smaller than, first let me take the situation where small r is less than capital R. So, if this is my capacitor plate, I take a point which is in between the capacitor plates of a distance small r, that is capital R. The electric field is pointing downward. So, I take a loop of integration like this, and I use this formula. Now, between, so I have, so what I will do is I take a, this is my path of integration, and I take this surface, the simplest surface, again just like before, I take this surface. So, I take the surface. So, because of symmetry, B is azimuthal. So, integral B dot dl is nothing but B times 2 pi r, and the electric flux is equal to the area of this pi r square into electric field, which is E. E is nothing but sigma by epsilon 0. Sigma is nothing but the surface charge density, which is q by area of the plates, which is q by pi capital R square. So, this is equal to pi small r square by epsilon 0, 1 by pi capital R square q, and that is equal to q times r square by epsilon 0 r square. That is the electric flux passing through this surface which I have taken, and so d phi E by dt is nothing but r square by epsilon 0 r square dq by dt, and dq by dt is nothing but the current which is flowing through the wires. So, epsilon 0 r square into I. So, the rate of change of electric flux through this surface is nothing but small r square by epsilon 0 capital R square into I, and so if I substitute into the Ampere's law. So, for this loop, for example, for this surface there is no conduction current. This is a surface which is taken between the plates of the capacitor. So, there is no conduction current passing. So, I have the two plates of the capacitor and my area of integration is here, and the current is flowing through a wire from here and getting out from here. So, there is no conduction current, there is only displacement current. So, if I use this formula, so in the presence of only displacement current, so I have actually mu 0 times I c plus mu 0 epsilon 0 d phi e by dt. For this loop which I have taken, this is equal to 0. So, this becomes simply mu 0 epsilon 0 d phi e by dt, which is equal to mu 0 epsilon 0 d phi e by dt I have just now calculated, r square by epsilon 0 r square into I, and the left hand side I have done as b into 2 pi r. So, b becomes equal to mu naught r by 2 pi r square into I. This is for r less than r. So, if the distance from the axis of the circular plate capacitor is less than capital R, which is the radius of the capacitor plates, and I am inside in the space between the capacitor plates, there is a magnetic field associated with the changing electric field, and that magnetic field comes out to be mu naught r by 2 pi r square into I. Now, I leave this as a problem to you, that you can show that if you take a conductor of radius capital R, that is the axis, and if you calculate the magnetic field at a distance r from the axis within the conductor, you will get exactly the same expression as this. So, I leave this problem to you to show that this is exactly the same as if there was an actual current, conduction current flowing through a wire of radius capital R, and you are calculating the magnetic field at a distance small r from the axis of that conductor. So, that was the magnetic field inside the capacitor plates, and for r greater than r, which means this is my capacitor plates, electric field is pointing downward here again, and I take a path outside. So, this is my distance r. So, again now phi e is equal to, now please remember the electric flux is only present in the radius capital R. So, pi r square into E, which is equal to pi r square into sigma by epsilon 0, and sigma into pi r square is nothing but q, because pi r square is the area between the plates of the plates times the charge density is the total charge. So, d phi e by dt for this case becomes equal to 1 by epsilon 0 dq by dt, which is nothing but 1 by epsilon 0 times I. So, if I use Ampere's law, I will, so if I use this law, B dot dl is equal to mu 0 I c plus mu 0 epsilon 0 d phi e by dt. This is again 0, there is no conduction current passing through this area, and the second term is the displacement current which I will get, and if I use that, I will get B into 2 pi r is equal to mu naught epsilon naught into q by epsilon d 1 by epsilon 0 d q by dt, which is equal to mu naught into I, because dq by dt is the current that is passing through. So, the magnetic field happens to be mu naught I by 2 pi r. This is for r greater than r. So, if I had this capacitor plate like this here, for points between these within this region, B is given by this value mu naught r by 2 pi r square I. So, the magnetic field on the axis is 0, small r is 0, and as you move away from the axis, the magnetic field increases linearly with the distance until it reaches the distance capital R. Beyond capital R, the magnetic field decreases as 1 by r. So, if I were to plot magnetic field as a function of position between the capacitor plates, this is R, this is B, and suppose this distance is capital R, till here the magnetic field increases linearly and then decreases 1 by R. And please note that the magnetic field is continuous at small r is equal to capital R. So, magnetic field at small r is equal to capital R is equal to mu naught I by 2 pi R. Also note that, so this is the magnetic field as I have calculated, say at this point at a distance small r from the axis. This is also the same as the magnetic field at a distance small r from the axis above the conducting wire, because what you would have done, you would have taken an Amperian loop around this. The current that is passing through is purely conduction current, which is I, and you would have got exactly the same result. So, magnetic field, whether you calculate using this conduction current passing through the surface or the displacement current passing through the surface, you get the same value. And so, this is that additional term which has been introduced by Maxwell is a very, very important term, as it makes the Ampere's law consistent with no matter what surface you take to calculate the current enclosed by the surface. So, the current enclosed could consist of either conduction current or displacement current, and so I have to take into account both these currents. Now, I just want to look at this, continue to look at the same problem. So, I had this capacitor plates and I was trying to find out the magnetic field at this point, which is within the area of the capacitor plate. This is the capacitor plate here, and that is my so electric field. So, current is flowing like this here, current is flowing out from here, and the electric field lines are like this. So, I do an integration like this. Now, as I told you, this is the Ampere's law simply tells me B dot dl is equal to mu naught I c plus mu naught epsilon 0 d phi e by dt. Now, I had taken this area for my integration. I had taken this area between the circular area that is lying between the within the loop, but again as before I am not constrained to take that area. I could have taken another area which looks like this. So, I could have taken the surface area to be outside. So, this is like a cylinder, this is like a cylindrical surface here, and this is the cylinder here. So, it is a cylinder with a hole here. So, I could have chosen this surface area rather than the surface area which is flat surface area which contains a circle as its boundary. Just like in my earlier discussion, remember in my earlier discussion I said that when I have to calculate the current enclosed by this, I can take this surface area or this surface area, and I got the same result. So, here also I can do the same thing. I can take this surface area, which is the flat surface area, to calculate the magnetic field at this plane, at this point between the pair of capacitor plates, or I could have taken a surface area outside. So, I want to check whether I get the same result, and you will see that I will get the same result because the equation is right. So, now what happens in this case is there are both currents present in my problem, because this surface now includes this surface in which the conductor is passing. So, there is current I entering this surface here, and there is a current so there is a conduction current entering this surface, this volume, and there is a displacement current leaving this volume. So, if I do my integration like this, please remember I have always mentioned that in this integral the area over which, so how do I define whether the current crossing the area is positive or negative? So, if I integrate like this in my loop of integration, according to right hand rule, this implies this is my right hand direction. So, current enclosed will be positive if it enters like this, and current will be negative if it enters like this, if my loop of integration is like this. So, remember if I integrate like this, then the one which is coming towards me is a positive current, the one which is going away from me is a negative current. On the other hand, if I integrate like this, so if my line integral is taken like this, then the positive current implies current going towards you and negative current implies current coming towards me because of the right hand rule. So, I must be very careful. So, here because I am integrating in this figure in this direction, so positive surface area, positive area will be away from this. So, here this area vector, the normal to the area is actually like this. Because of the area that I have taken, because of the closed loop that I have taken, the area integral, which that means whether the current entering is positive or negative depends on the direction of the normal or the area, and that normal I must choose judiciously. So, now what happens in this problem is there is on this surface area there is conduction current entering from this point, there is no current anywhere except in this region, in the cylindrical region between small r and capital R. So, there are two currents now, conduction current I, IC is equal to I, and displacement current between R and R plus dr, R plus R. So, sorry, between R and R. So, between this radius, so if I look from the side, if I look, so that is my capacitor plate and that is the distance which I am calculating. Here is where I am calculating the magnetic field. So, this is small r, and so the area actually consists of, so the area let me draw here, the area consists of a plane going outside the plates. So, this is the total area, the area of integration is here. So, as you can see here, that is the loop in which I am integrating. So, if the electric field is pointing downward, so in this case if I plot the, if I am drawing like this, the electric field is pointing towards me in this region only, this is capital R. So, the flux that is actually responsible or the current which is entering is only in this area, because that is my area of integration, that is the area which is this, which is contained in the surface, that because I am integrating over this, and the surface which I have chosen is not the standard surface, which is the flat surface of which this is a boundary. I have taken a surface which is outside, and so there are two kinds of currents in this problem. Now, there is a conduction current entering from here, and there is a displacement current that is passing through the surface between the radius small r and capital R. So, I have to consider both currents in this equation, which is B dot dl, again let me write, is equal to mu naught I conduction plus mu naught epsilon naught d by E by dt. I must consider both of them. So, in this for this surface I c is equal to I, and I must calculate the displacement current I d. And displacement current is nothing but epsilon 0 d phi E by dt. So, I d is equal to epsilon 0 d phi E by dt. Now, here is where the problem appears, that because of the direction of integration, the normal is in this direction and the electric field is pointing away from the surface, outside the surface, and the area is the area vector is towards the surface. So, I will get a negative sign in the integration. So, what I will get is this is equal to epsilon 0 d by dt of minus of electric field into this area. I am assuming electric field to be uniform between the capacitor plates and there is no electric field outside. So, electric field is uniform and the area is nothing but pi capital R square minus pi small r square. So, this is equal to pi times capital R square minus small r square, which is equal to epsilon 0 d by dt of minus sigma by epsilon 0 pi r square minus r square, which is equal to minus d by dt. Now, sigma is q by a into pi into r square minus r square, which is equal to minus pi by, now area is pi r square into r square minus r square into dq by dt, which is equal to minus I times dq by dt is I, pi cancels off and I get 1 minus r square by r square. So, there is a displacement current of minus I times 1 minus r square by capital R square. There is a displacement current of minus I times 1 minus small r square by capital R square that is crossing this part of the surface. There is no other current in any other surface except from here there is a conduction current entering. So, the total current that is entering now consists of these two parts. So, if I now use integral, I need to use now the Ampere's law, B dot dl is equal to mu 0 times I conduction plus mu 0 times I displacement, and so B into 2 pi r is equal to mu naught I. Now, that was the conduction current, and displacement current is this thing. So, minus mu naught I into 1 minus r square by capital R square, which is equal to mu naught I minus mu naught I plus mu naught I times r square by capital R square. So, this cancels off and this becomes equal to mu naught I into small r square by capital R square. So, B becomes is equal to mu naught I small r square by capital R square into 1 by 2 pi r, which is equal to mu naught I r by 2 pi r square. So, let me compare this with what we had obtained earlier for the position r less than r, and that is the formula here, mu naught I r by 2 pi r square, exactly the same equation. So, irrespective of what surface I choose, I must get the same value of magnetic field, and I have shown that through this example that it is not necessary that I must choose a surface which is only carrying conduction current. I could choose a surface which only carries conduction current, I could choose a surface which only carries displacement current, or I could choose a surface which carries both conduction current and displacement current. And so, in this example, it shows that if I take a surface which I have now taken in this example, in this example the current that is entering the surface or crossing the surface contains both conduction current and displacement current, and as I showed you, I must be very careful in taking the right signs for the currents, because whether the current is entering or leaving the surface depends on the direction of the area of the surface, and this one must choose appropriately and carefully in these calculations. So, this was an example which I wanted to discuss to show you that it is possible in problems to have both kinds of currents, both conduction and displacement current densities. So, let me take an example here. So, let me take a capacitor with R is equal to 1 centimeter carrying a current of 1 amperes. At any given time there is a current of 1 ampere flowing through the capacitor plates to the capacitor. So, for R less than R, let me calculate. So, R is equal to, let me take 0.5 centimeter, magnetic field is given by mu naught R by 2 pi r square into I. So, this is equal to 4 pi 10 to the minus 7 into small r is 0.5 10 to the minus 2 meters into current is 1 ampere divided by 2 pi into 10 to the minus 4 r square, and that it comes out to be 10 to the minus 5 Tesla. So, there is about, this is 10 micro Tesla. Micro is 10 to the minus 6, that is 10 micro Tesla, that is the magnetic field at a distance of 0.5 centimeters from the axis of the capacitor plates. So, please see that although I am only passing a current and generating an electric field between the capacitor plates, the changing electric field is creating a change in electric flux, and that changing electric flux creates a magnetic field, and that magnetic field happens to be about 10 microtesla here. Now, if I want to calculate for a point outside the capacitor plates, so let me take for example r is equal to 5 centimeters, the magnetic field B is equal to, so that I must use the other formula now, mu naught I by 2 pi r. So, that is the formula which I must use now. So, that is mu naught I by 2 pi r. So, this is equal to 4 pi 10 to the minus 7 into 1 ampere divided by 2 pi into 5 into 10 to the minus 2. That comes out to be 4 microtesla. Okay, so that's the magnetic field at a distance of 5 centimeters on the capacitor plates. You can also calculate at a distance of 5 centimeter from the wire that is charging the capacitor, and you will get the same magnetic field outside the wire at a distance of 5 centimeters from the wire. So, this example tells me that I can actually use this to calculate the magnetic field between the capacitor plates. Now, please remember, I could calculate the magnetic field simply because of symmetry. This equation is always valid. This equation, modified form of Ampere's law, is always valid. In situations where there is symmetry, I can actually calculate the left hand side and take magnetic field outside the integral and obtain the magnetic field value. But if there is no symmetry, I would have to do an integration over an appropriate path to actually calculate the magnetic field. So, please remember that this equation is always valid. It is very useful in situations where there is symmetry in the problem and I can calculate the magnetic field. So, let me leave a problem to you to work out. A parallel plate capacitor air filled is getting charged and the current at a specific time is 0.45 amperes. If radius of the plates r is equal to 5 centimeters, A, calculate the total displacement current between the capacitor plates. B, calculate the displacement current density and C, calculate the magnetic field B at r is equal to 2.5 centimeter and r is equal to 10 centimeter. So, please try out this problem. A parallel plate capacitor which is air filled is getting charged, and at any given instant of time the current is about 0.45 amperes and the radius of the capacitor plates is given. So, please calculate the total displacement current passing through the plates, the displacement current density, and calculate the magnetic field at a distance 2.5 centimeters from the axis and at a distance of 10 centimeters from the axis. Now, let us recall, we have now discussed almost all the basic requirements in electromagnetism. Now, before we move on, I just want to recall the Faraday's law of induction and the Ampere's law. So, in Faraday's law we obtain this equation integral E dot dl is equal to minus d phi b by dt. The rate of change of magnetic flux, this is equal to minus d by dt of integral b dot dA. Time rate of change of magnetic flux leads to an electric field. Modified Ampere's law. So, let me look at a situation where there is no conduction current, there is a region of space where there is electric and magnetic fields. So, when there is a magnetic field in a region, then the rate of change of magnetic field gives you an electric field, and with I am looking at a region with conduction current is equal to 0, I will get integral b dot dl is equal to mu naught epsilon naught d phi e by dt, which is equal to mu naught epsilon naught d by dt of integral E dot dA. Rate of change of magnetic flux leads to electric field, rate of change of electric flux leads to magnetic field. So, you see Maxwell's addition of this term into this equation has coupled the electric and magnetic fields. If you have a magnetic field and in a region of space which is changing with time, it will lead you to an electric field which may be varying with time, and if the electric field varies with time, then it will lead to a magnetic field. So, this magnetic field couples to the other earlier magnetic field, and we get a set of coupled equations. So, electric field, time varying electric field generating magnetic fields, time varying magnetic field generating electric field, and so the electric and magnetic field get coupled through these two equations. So, the addition of this term was extremely important, and what has happened now is it has become symmetric. There is a bit of symmetry in these equations now, because changing magnetic fields produce electric fields, changing electric fields produce magnetic fields, and this symmetry is beautiful in these equations, and as we will see that this presence of this term leads to a very, very important prediction from here, which is the existence of electromagnetic waves. So, Maxwell when he put in these equations found that these equations which I will write down a little later show the existence of new types of waves called electromagnetic waves, which are nothing but waves of electric and magnetic fields. Now, before we do that, let me try to draw a figure representing these two equations. So, if I take a region of space, for example, here the magnetic field is say pointing downward, uniform and magnetic field pointing downward. Then if I take a loop like this, suppose the magnetic field is increasing with time. So, the magnetic flux is increasing with time in this direction. So, what will be according to Lenz's law? There is an electric field which is induced, which will be like this. The current, there will be current like this, so that it opposes. So, this is the direction. So, these are the magnetic field lines, this is B field and this is the E field. So, if the magnetic flux is increasing with time pointing downward and increasing with time, because of the minus sign here, because of the negative sign here, the induced electric field will be in this direction to oppose the change in the magnetic field. If I take a corresponding problem and if I had electric field pointing downward, and the electric field, so this is the electric field, and the electric field was changing with time, and if I take another loop like this, the direction of induced electric field will be like this. So, that is the magnetic field, sorry, this is magnetic field. So, magnetic field pointing downward increasing with time leads to an increasing magnetic flux in this loop, and because the magnetic field is pointing downward, the induced electric field will be anticlockwise. Here, if there is an electric field pointing downward and electric field is increasing with time, then the induced magnetic field will be clockwise. So, there is a small difference in these two, and that difference comes in primarily because of the presence of this negative sign in this equation. There is no negative sign in this equation. Of course, there are extra terms sitting here, but there is no negative sign here and there is a negative sign here, and that leads to two different situations here of oppositely directed electric field generated by magnetic field, changing magnetic field, and the corresponding magnetic field generated by electric fields. Now, I want to take an example, I want to show an example of a comparison between conduction current and displacement current. Now, in an earlier class you must have studied about conduction through wires and you have studied about RC circuits and so on. So, we define, remember at that time we had defined a conduction current density Jc is equal to sigma times E. The conduction magnitude of the correct conduction current density is given by sigma E, sigma is called the conductivity. So, sigma defines the conductivity of the medium and the conduction current density is proportional to the electric field, and that is the sigma is conduction current density. We had obtained in this lecture a displacement current density J d of epsilon 0 d E by d t. So, that was free space. Now, without going into discussion, I would like to mention here that if there is a medium, then the displacement current density becomes epsilon d E by d t. I replace the permittivity of free space epsilon 0 by permittivity of the medium, which is epsilon, and epsilon is nothing but epsilon 0 into dielectric constant. Remember, this is the epsilon is equal to epsilon 0 into dielectric constant k. So, if there is a medium, the displacement current density in the medium is given by J d is equal to epsilon d E by d t. The conduction current density is given by sigma times E. So, I could have media in which there is they are partly conducting, they are not perfect conductors, they are conducting, and they also have a displacement current. So, I could have situations where the medium carries both displacement current and conduction current. So, let me look at an example. So, as an example first, so if I look at the ratio of these two, I want to look at the ratio of these two. So, let me take an electric field which varies as say E 0 cos omega t. So, I have an electric field which is oscillating with time at frequency omega. So, the conduction current density will be sigma E, which is equal to sigma E 0 cos omega t. The displacement current density is equal to epsilon d E by d t, which is equal to minus epsilon omega E naught sin omega t. So, I differentiate this with respect to time, I get minus omega E naught sin omega t. So, that is the displacement current density, the conduction current density. The first thing that you notice is the conduction current density and the displacement current density are not in phase. There is a minus sign here, and this is cosine of a cosine function of time, this is a sine function of time. So, if I plot for example as a function of time, so let me plot for example first the conduction current density. So, the conduction current is cos omega t. So, one cycle if I plot, that is the conduction current. So, displacement current is minus this thing. So, let me, these are the values here. So, what this will be? This will be going like this. This is the displacement current. This is cosine function of time, this is minus sine function of time. So, you can see here that there is a phase difference between the conduction current and the displacement current, and this becomes an important consideration in some advanced courses that you will be studying a little later in your career. So, this is the displacement current density and that is the conduction current density. So, I can actually calculate what is the maximum value of conduction current density and compare it with the maximum value of displacement current density. So, the maximum value of conduction current density J C max is equal to sigma E 0 and J D max is equal to epsilon omega E 0. Maximum value of conduction current density will appear when cos omega t is 1, that is sigma E 0, and maximum value of displacement current density will happen when sin omega t is minus 1, and that is epsilon omega E 0. So, the ratio of conduction current to or displacement current to conduction current is equal to the maximum value epsilon omega E 0 by sigma E 0, which is equal to epsilon omega by sigma. So, that is a ratio of the displacement current to conduction current, and omega is actually in terms of frequency I can write this 2 pi nu epsilon by sigma, where omega is equal to 2 pi nu. Omega is the angular frequency, nu is the frequency, and omega is the angular frequency. So, let me take two examples. One, I take a good conductor. So, in a good conductor, the conductivity is approximately 10 to the power 7 moles per meter. It is a large conductivity. So, that is what is called a conductor, it is a very large value, and if I take a frequency of say 1 gigahertz, remember we had introduced this power 10 to the power 9, which is called a gigahertz, then and for good conductors epsilon is approximately equal to epsilon 0, and I can calculate J D by J C, which is equal to 2 pi 10 to the power 9 into epsilon, which is 8.85 10 to the minus 12 divided by sigma, which is 10 to the power 7, and that comes out to be 5.6 into 10 to the power minus 9. So, you can see here that for a good conductor the majority of current is conduction current, the displacement current is negligible in compared to the conduction current density. So, the current that is flowing through a conductor is primarily conduction current, and there is hardly any displacement current, and that is why it is called a good conductor. It is a conductor because much of the current that is flowing through this medium is because of conduction current and not displacement current. Let me take a poor conductor. Such as seawater. So, seawater has epsilon is equal to 81 times epsilon 0, and sigma is approximately 4 moles per meter, and so J D by J C is equal to, so this is 2 pi into frequency 10 to the power 9 hertz into epsilon, which is 81 times 8.85 10 to the minus 12 divided by sigma, which is 4, and that is about 1.1. So, at the frequency of, so the frequency which I am taking is 10 to the power 9 hertz. So, at this frequency seawater, when you propagate this frequency of a wave through a seawater, there is almost equal contribution of conduction current and displacement current passing through seawater. Please note that this ratio depends on frequency. So, at higher and higher frequencies this term can start to increase, and at lower and lower frequency this term will start to decrease. So, depending on this ratio of displacement to conduction current, you can have different situations. So, if you have a situation where sigma is much greater than omega epsilon, when sigma is much greater than omega epsilon, then conduction current is much greater than displacement current, then this behaves as a conductor, and if sigma is much less than omega epsilon, then this behaves as a dielectric. So, depending on the frequency and the properties of the medium in terms of conductivity and epsilon, a medium could behave as a conductor where the conduction current is much bigger than displacement current, or behave like a dielectric in which the conduction current is negligible compared to displacement current. So, I can have both these limits, and it depends on frequency. So, I leave it to you to look at the same problem. Please calculate this ratio at frequency say 1 megahertz, which is 10 to the power 6 hertz, and say 100 gigahertz, which is much higher frequency. So, you will see the difference in this ratio, because this ratio is approximately 1 around 1 gigahertz. So, as you will see, for lower and higher frequencies, the same medium can behave either as a conductor or as a dielectric. So, this is a very important consideration of these two. So, let me just write down before we close the 4 equations that we have obtained till now, which are Maxwell's equations. Integral E dot dA is equal to charge enclosed by epsilon 0. Integral B dot dA is equal to 0. Integral E dot dL is equal to minus d by dt of integral B dot dA. Integral B dot dL is equal to mu naught I c conduction current plus mu naught epsilon naught d by dt of integral E dot dA. The 4 very important Maxwell's equations. I will stop my lecture here, and what we will do in the next class is to look at these equations, and I will show you that these equations predict the existence of what are called as electromagnetic waves. And that was a very important discovery and a very important contribution of James Clerk Maxwell, when he showed that these equations predict the existence of electromagnetic waves, and light is a form of electromagnetic wave. And so, these are called Maxwell's equations. So, I will stop my lecture here, and we will continue with the discussion in the next lecture. Thank you very much.